Hello.
Hi, Mohammed. How are you?
Good, good. How are you?
Good to see you. Thanks. I'm good.
That's great. That's great. So can
So
you
can
see
you
me?
just before we get started, can you just um try to make sure you would be able to share your screen?
Sure. Okay. Can you see my screen now?
Yes, we can see your screen.
That's great.
All right. Um, so whenever you are ready, we can just get started. Maybe,
Sure. I'm ready. If you want to wait a few,
yeah, just
I'm
one
not
more
sure how many.
minute. Yeah, one more
Yeah,
minute.
sure.
Yeah, people are joining. All right. Um, Hi everyone. Welcome today. It's a pleasure to have Mohammed Mehraban. Mohammed is a researcher at London South Bank University at UK. Um, so we have an interesting topic, and I invited Mohammed to talk for us a little bit about the potential of transfer learning. Transfer learning is a data science method, so he's going to explain a little bit in general about transfer learning, and we see an application area for transfer learning that has been applied in Muhammad's research. Um, so without further ado, Muhammad, field is yours. So you would be interested to learn more about transfer learning and your research.
Thank you. Thank you very much. So, hello everyone. My name is Mohammed. As Shayan said, I'm a researcher at London South Bank University. Um, Thank you for coming to this session. So today I want to talk about transfer learning as a tools for improving building energy prediction across climates and building types to address the data scarcity challenge. Uh, Even though my area of research is building energy prediction, but your research might be different. So, or maybe the course you're studying. So don't worry. I want to give you different examples so you will understand the concept of transfer learning. Then you can apply it to your area of research or whatever you're doing in your um, research. So let's start. Let's start with the challenge. So actually, what is the first requirement for accurate AI prediction in buildings or in any different area? So that's data, but it's not every data. The data that we're looking for is very important because it needs to be high quality. It needs to be sufficient. The amount should be sufficient in order for AI model to train very well. And also it should be relevant to the target problem that we're looking to solve or predict. So now I'm going to talk a little bit more about data. How can we use the data for AI training and prediction? So I'm pretty much sure that you already familiar with training and testing set, which is part of the data curation. So training set is part of the data set that we feed into the model to train it, to understand what's the relationship between feature and targets. And when the AI model is trained and successfully trained, we can use the testing set in order to evaluate the performance of the model trained. So As you see here, we have training set. It has two parts, feature and targets. Features are the input part of the data we feed into the model, and targets are the result or the prediction that we want the model to give back to us. So when the model is trained, then we go straight for prediction. For prediction, we need, as I said, testing set, but not all of it. The features part of it as an input, we pass it through the model, and we have predicted target. Then we can compare the predicted target to the actual value to understand the performance of the AI model trained. So here is the basic overview of how we can data for training and prediction. But I want to give you some example of how these features and targets are. For example, in building performance, the area that I'm working on, the features can be building envelope properties. For example, different types of wall, windows, roofs, etc. When they have different values in terms of thicknesses, in terms of material, U value, and etc. We can use them all as an input. And then we have indoor environment data. It could be indoor temperature, relative humidity, CO2, or any other information that we're looking for. Maybe occupant behavior, the number of occupants, their behavior in terms of natural ventilation, heating schedules, or cooking, showering, because they are important in terms of building simulation. Also outdoor data, they can be climate, they can be city or country, or even shorter, like outdoor environment data, like humidity, temperature, and etc. Or any different type of data that we can have in buildings, like area, ceiling height, and etc. And we can predict indoor temperature, thermal comfort, heating load, cooling load, energy cost, energy use, mold risk, and etc. So I hope you understand that what I'm talking about, because data is very important. We need to know what feature and targets are. Now, how we gonna get the building related data? So this is another important part. So we can get the data from simulation. So we can create different scenario with combination of different inputs, do the simulation, get the data, and then we can train an AI model. Another thing is IoT sensors. So we can install sensors in the building to get the indoor environment data, and then we can use it as our data, or even inspection and or surveys. But the problem is data collection might be consuming, very time consuming, or even maybe costly, or even labor intense, or in some cases, it might not be even possible. So it's very important to have in mind. So the challenge of data collection. That's why we're trying to solve this issue with transfer learning. Okay, let's move on. Imagine you already have a rich data set that it might be slow to collect or costly or anything, but imagine you already have it and you already train an AI model with high accuracy prediction. Okay. Now you want to use it for a new context, for example, a new building or a new climate or a new city, whatever. And in the new environment, fresh data might not be exist or might be time consuming or costly to collect. And you still need fast decision. So full data collection is not possible. For example, you're working on a conceptual design and you want to see different combination of the inputs I mentioned in terms of building energy performance, and you don't have time to do all the simulation. So you need to make decision as fast as possible. So that's why we are trying to use transfer learning as the best approach here. Sorry. Okay. What is transfer learning? Basically, the goal is we need a strategy that can use knowledge from previous data set, previous city, previous climate, or previous anything that you're working on without rebuilding the model from scratch. So we already trained a strong model in one data-rich context, and then we adapt it to new context that has only like a tiny section of the data. So that's the goal. I hope you understand it, but before you go through the examples with more details, and you will the concept of transfer learning. Okay, this is the workflow that I'm going to go walk you through. So basically, start with the source data set, baseline model, new data set, zero-shot transfer, similarity score, and different type of transfer learning techniques. I'm gonna talk about the latest research that I have done in terms of building energy performance. So the data was 11,000 energy plus scenarios which were simulated using London climate. So take a look at the United Kingdom map. London is here, so basically we ran a huge scenario simulations, like 11,000 scenario. It took like many days to be completed, although I used automation, but still it was time consuming. But it was only related to London climate. Let's talk about the inputs. So we cover 4 types of building as detached houses, semi-detached, attached, and apartment, 9 type of walls, 4 types of internal walls, 8 type of roofs, 22 types of windows, window to wall ratio ranging from 0 to 100%, ceiling height of 2 to 4 meters, floor area. As you can see, different parameters, infiltration rates, occupancy, and output simulation where energy use intensity, thermal comfort, and heating load. Actually, I calculated cooling load as well, but in London, it wasn't that critical, so we decided to remove it. So the outputs were these 3. Okay, now here is an example of the data. As you can see, these are the inputs, different values, and these are the outputs, the target that we're looking for prediction. Okay. Now let's talk about the model we developed at the moment. So basically, the model has 3 components. One is gradient boosting machine, or GBM. The other one is extreme gradient boosting, or XGBoost. And the third component was a feed-forward neural network, or FNN. So I'm sure that you're already familiar with GBM, but I want to walk you through it just shortly. So GBM is an ensemble method that builds a series of small decision trees. So we give it training data, it makes the first prediction. Definitely the prediction has errors, so we have residual, we pass the residual to the next tree. We do it again and again in order to reduce the amount of errors. And each new tree learns the errors of the previous model. Trees are added one after another sequentially, so each improving the models a little. And the output would be the sum of all small corrections. This gives a strong, accurate model that improves step by step. That's how GBM works. And the second component is for feed-forward neural network. So basically, this is a deep learning model that uses many layers to learn complex patterns. So information flows forward through neurons from left to right, as you can see here. We have different layers. The first layer is input layer. So as you can see here, we have 10 neurons. And these 10 neurons are actually here, the 10 inputs that we have. So they are those ones. And here. And then we have an output layer which has 3 neurons, which are the outputs that we want the model to predict for us. And also it has 7 layers. So why we said deep learning? Because if it has more than 2 layers, it's going to be deep. And why my model has 7 hidden layers? Because basically it's part of the optimization process. So I calculated using Bayesian optimization, but you can work with any optimization technique you already know, like grid search or whatever. So here is how the effect works.
So Mohammed, number of layer is essentially one of the hyperparameter that you
Exactly.
optimize.
Yeah. And also in each layer, we have different neurons as well. So in this case, we have 58 neurons in each layer. So again, that's part of the hyperparameter optimization. So let's keep moving forward. The last point is extreme gradient boosting, or XGB. So basically, is pretty much similar to GBM, but has a stronger optimization techniques that can create trees in parallel. So training time would be much faster, and the prediction actually is very high accurate. So here are the templates, but how I used it in my study. So basically, here is the training data. We pass it through the first model, which is FNN. We got the prediction. And again, we passed through the XGB. We got the prediction. So here is a technique that's used called the stacking. So basically, we passed the prediction of both model to another model, which called meta learner. So I use GBM in this case here. So we passed the prediction of those model, and we get a new prediction based on those previous models. And let me show you here. So FNN produces one prediction stream, as you can see here. XGB produces another stream here. A GBM meta learner takes both prediction as input and produces final prediction. Okay, so let me show you the result now. The result of XGB, as you can see here, is like 98% accuracy in terms of R squared. FNN is 91. And when we stack the both model into the one unified hybrid model, we can see the errors dropped a little bit, and also the accuracy improved. Okay, now let's move on. Okay, as I said before, we did all the simulation for London climate, okay? And we created this model. We trained this model only based on London data that we got. Now I'm thinking, so what would happen if we apply this model, which is trained specifically on London data set? What would happen if we apply to other climates with different weather and different outputs, different parameters? So let's see. For this reason, I did the same process in order to create more data for different cities across the UK. For example, I included 15 major UK cities like Manchester, Liverpool, and etc., and created 1,000 scenarios for each in order to test the performance of model trained on London on other cities. Okay, let's see the results. Here is the zero-shot transfer. So here you can see the result of the model when it tested on different cities. So in some cities like Nottingham, Liverpool, or Cambridge, the result is not bad. Actually, it's higher than like 85% in terms of R squared. But in some cities like Belfast or Edinburgh, we have like 14% or 13%, which is not good. And here is the average result in terms of all the climates. As you can see, if we test the model in a new data set, we can see that R square is like 71%, and we have higher amount of errors. So that is, now we want to focus on this to solve the issue using transfer learning to improve the performance of model in different climates. Okay.
Mohammed,
The first
I'm
thing,
sorry to interrupt you. Can you
no worries.
explain again the zero shot transfer? Because in the slide you were explaining that you got a little bit disconnected, not the results. Why you are applying a zero shot transfer? What
Okay,
is the
so
importance of that?
zero shot transfer means that we get the model which is trained on London, and we pass just the data of other city to it without anything else. We just test the other cities' data on the model which is developed on specifically on London dataset. So I'm not sure if you get it. It doesn't make sense, or yeah. Okay, so let's move on. Okay, to understand this, we try to understand the different climates of London and compare to a UK city that we consider in this study. So we've got the mean, max, and average temperature and humidity, and we try to formula to create a similarity score. And the concept is to see if which cities are most similar to London climate in terms of temperature and humidity. Okay, so definitely London is number one. One maximum similarity, and zero is the lowest amount of similarity. And as you can see here, some of the cities has the highest amount of similarity in terms of climate to London, and some of them are not. And for example, let's see, we have Brighton, Edinburgh, Belfast as the lowest amount of similarity. And if we go back and take a look transfer, we can see these cities have the lowest amount of accuracy in terms of prediction. So now we want to work on this to have a model which can predict on other cities as well with high accuracy. So that's why I'm going to go through different transfer learning techniques. Let's start with the first one. The first one is instance-based transfer learning, or IBTL. So imagine we have source data, London in this case. It is a large data set, and let us train a strong model like we did so far. Okay. Now we have a target data like Manchester, as you can see here. That is a small, and we cannot train a new model from scratch using those data. So in this case, we want to use instant-based transfer learning. But with this technique, we do not retrain the model using target data set. But what we're going to do, instead, the target data help us find which rows inside the London data set look close to Manchester. So basically, we want to compare those data sets to find out which rows of those, which data points of London is similar to Manchester. So when we compare them, then we keep only the similar rows from London and ignore the rest. So then we pass it through the model. So this is the first and transfer we can use. So we can select part of London data that is most similar to Manchester and ignore the rest. Now, let me to show you in more details. Here is the data set, London and source data set, and here is the target data set, which is Manchester. Okay. Each of these points are a row in the data set. What we're going to do in this box, we compare each row of London to every row in Manchester data set. Okay. And then we're trying to find the distance between them. So it has the calculation, so I can show you later. And then we're going to use something called k-nearest neighbors. So basically, we're trying to understand, for example, the top 20 rows in Manchester, which is similar to this point. After this, we have every row in London data and the average distance of that row to the most similar data set in London, okay? When we have that, we can rank the London data set. As you can see here, the top ones are the most similar to Manchester data set, and these ones are the least similar. So we can ignore them, remove them from our data set, and keep the top n% of most similar rows to this target city. So this n can be like 25%, whatever, it depends on the project. Then again, now we have a new data set, which is again London data set, but a new subset of it. And then we pass it through the first components of the baseline model, FNN and XGB, which gives us this stacked features. And then we pass the prediction through the GBM. Again, here we fine tune the GBM using new subset, optimize the hyperparameters to get the highest amount of prediction accuracy. So with this method, the IBTL, as you can see, I use K20, which means top 20 rows similar to London for each row, and N 75%. The accuracy improved by 2.6%, and errors reduced by 1.4%. But it's not that, but still improvement. Okay, let's move on to the next technique. which is domain adaptation transfer learning. Imagine we have a source data London, which is large and enough to train a strong model. Again, we have another data set, Manchester, which has a different numerical style. So the London model cannot predict well on it, okay? So it has, for example, or different variants, but when we pass this new data to the London model, its prediction is pretty bad. So what we're going to do in this technique, domain adaptation, again, we do not train the model using target data. What we're going to do instead, we transform the Manchester data so it follows the same numerical style as London, like same mean, same covariance, same correlation. We're trying to reshape the Manchester data to make it more similar to London. After alignment, the Manchester data becomes London-like, which allows the London trained model to make accurate predictions. So we normalize the target variability and apply source covariance to align target features. Okay. Now they look like. So let's move on to show you in more details. Again, here is the source and target data. We compute the mean and covariance of London and target city. Okay. And then what we do, then we subtract the mean from the target data, so the value moves around 0, which call it centering. In the next step, we multiply the center data by the inverse square root of the target covariance to remove the target variance, and which called tightening. And also then we multiply it by the square root of the London covariance to apply the variance and correlation pattern of London. And at the end, finally, we add the London mean to shift the data to the same center as London. So basically, as you can see, we're trying to reshape the target data to make it more look like London. And don't worry about the calculation. There are different it shouldn't be this one. So again, we pass this new data through the model, get a prediction, and that's it. So basically, again, in this new technique, we do not retrain the model. We just try to reshape the style of our target data set to make it more look like our source domain. Okay, let's talk about now. The result of this one is a little bit better than previous one. As you can see here, the R squared improved, and now it's 79%, improved by 10.1%, and errors reduced by about like 20%, which is good. Now let's move on to the next one, which is parameter-based technique. Sorry. Okay, to summarize so far, IBTL keep only London samples similar to targets, and DITL make the targets data look like London. Let's move on to the type of transfer learning, which is parameter-based. So in our baseline model, we have 3 parameters, GBM, FNN, and XGB. And each of them can be fine-tuned. That's why we want to evaluate 3 parameter-based transfer learning techniques. Let's keep going. Okay. As I said, we have 2 model, XGB and FNN, which gives us the prediction, and we pass it through GBM. So what we're going to do here, we're going to freeze XGB and freeze FNN, but we want to fine-tune GBM, the meta learner head. So we're going to get like 1% of source data, for example, 110 rows of Manchester. If you remember, we had like 11,000 data for London, so 1% will be this. And then we pass it through FNN and XGB, we get the primary predictions, and then we try to pass it through GBM, but we're gonna fine-tune the GBM head in here. And this is the first time we're gonna retrain or fine-tune the that. Okay, and here is the result. As you can see, with fine-tuning the GBM head, actually the result is pretty good, and it's like about 91%. And the R squared improved by 26%, and error reduced by more than like 15%, which is great. The let me see what we have. Yep. The second parameter-based TL technique is freezing HGB and GBM head and fine-tuning the FN model. But we need to uh, consider something, that FNN is a deep learning model, and 110 rows, it's not enough for training the full layer. So that's why we need to do something else here. Instead of retraining or fine-tuning the whole layers, we want to freeze the first 5 hidden layer and just fine-tune partially the last 2 hidden layers. Because the early layers keep the strong knowledge learned from London, and the last 2 layers make a small correction, which is good for this new city. Basically, it can hold the knowledge that it learned so far, but we want to change it, modify it a little bit at the end. So again, we pass 1% of the data through FNN and XGB. We do fine tuning here as well and get the prediction, pass through GBM. Let's see what we get in this. This is not going well because the R squared we get is like 75%, which is 5.5% improvement compared to zero shot transfer. And also the error improved only by 1%. And the problem is because, again, it's a deep learning model which needs a higher amount of data set. And that's why the result is not good to GBM. Okay, let's move on to the third transfer learning techniques. So in this one, we're going to freeze GBM and FNN and try to fine-tune XGB head here. So again, we're going to use 1% of the data, pass through those models. We fine-tune XGB model here, so it includes also adding more trees as well. So we're going to hyperparameter. We're going to fine-tuning the hyperparameter, like an estimator number of the leaf, trees, and etc. And we get the primary prediction and pass it through GBM. And here is the result of this technique, which is similar to GBM, but a little bit higher with 26.6% accuracy improvement. And let's talk about the last technique that we want to explain, which is ensemble-based transfer learning technique. So in this technique, we do not touch or modify the London trained model. We keep it as it is, but we're going to try to add 2 more tiny models, one at the top of XGB and one at the top of GBM. So how it works? Basically, EBTL does not modify the original London model at all. The entire London model stays frozen. XGB, FNN, and GBM are kept untouched. Instead, EBTL adds small on top of the London to fix what London gets wrong for the target city. And the residuals or errors are true value minus London XGB prediction. So basically, we pass the 1% of the data through FNN, we get the prediction. Through XGB, we get the prediction, but it has error. Then we pass those errors through another XGB model to improve the prediction. So this shows how much the London XGB is incorrect for the target city. Small XGB is trying to predict the residual. And then we pass them through the GBM we had. Again, it has errors. And then we're trying to add a new model on top of the GBM to improve the prediction. So the first residual model corrects XGB outputs, and the second residual model corrects GBM meta learner outputs. So the final output would be London prediction plus learned correction. Let's move on. And here is the accuracy of the final method, which is ensemble based. And as you can see, it has the highest amount of accuracy with like 93.4% in R squared, and improved by 30% and more than 50% in errors. And also, I've done a little bit sensitivity analysis to target data as well. Um, the previous studies, the previous techniques that I mentioned were conducted using 1% of the data set, 1% of the source data set. And now we're going to repeat them with 1 to through 5%. As you can see, the accuracy improved in as we increase the number of data set. It's obvious, but after 1 to 2%, the rate is going down a little bit and getting stable as well. And we have the same trend in errors as well. So we can say with 1 to 2% of the data set, we can get the optimal result of the model in terms of transfer learning. Let's move on. And here is the runtime and efficiency analysis. As you can see, zero shot baseline, it take only 7 seconds because we didn't do any retraining or fine tuning. We just test the model using new data set. But ensemble-based models has the lowest amount of runtime, which is pretty good. They are very, light. We can add it on top of our learned model to improve the accuracy, and they demonstrated the highest amount of accuracy. But other methods, specifically parameter-based, they produced good accuracy, but actually it was very time-consuming. For example, fine-tuning GBM takes like 4 seconds, which is very high because it needs to go through all the data set to fine-tune it. But with ensemble base, we only need to create a new model using like 1% of the data. Okay, overall impact. Transfer learning improves cross-city prediction accuracy dramatically compared to zero-shot transfer. TL reduces data requirement by, I say, 98%, because with 1 or 2% of target samples, we can have a strong prediction. Also, you can adapt any predictive model to new context using just a few samples. It depends on your research. And it keeps the full, so let's talk about the ensemble technique. It keeps the full London model frozen and add the small correction models to fix the errors. This method is fast, stable, and highly data efficient from the result of this study. And lightweight adapters outperform full fine tuning, while cost fraction of computational time in this case was 26 seconds. So that's it. Thank you for listening.
Thank you, Muhammad. Let's
Sure.
open the floor for discussion and questions. Any questions?
Yeah, Rebecca and Paul, they raised hands.
No, I think they're just clapping for you.
Oh, yeah. That's great. Thank you.
No questions from the attendees?
I did a pretty good job then.
Okay, so I have a question about the application of transfer learning. So in this case, I mean, for this research project that you have done, um, you kind of, because you wanted to try this new machine learning method for building performance, so you essentially start looking at different type of transfer learning and see how well they can scale up the baseline model that you have already well trained. So the question would be, from what you have implemented in this research, what are the insight that you got in terms of what would be a practical way to think about what is the best way or what are the good combination of the transfer learning model for like a similar problem that we are working.
Exactly. That's a great question. So basically, we need to take a look at first the data set we have and the AI algorithm we developed because it's it's a huge amount of I can say research on it because it depends on the model you have. Because, for example, if you use GBM, so it's good to go for like ensemble based technique. But
Mhm.
if you're using deep learning models, you probably need different type of techniques to apply in your data set. So basically everything depends on the data set, the area of the research you're working, the AI model that you're using. But it's good to try different type of AI models first and try different techniques to see which one works best for you. And also, you always can optimize them using hyperparameter tuning to improve the accuracy as well.
Right. And I think, I mean, from my understanding, the kind of pre-processing step of looking and exploring the similarities between the climate condition for the specific problem that you were focusing on was also instrumental, right? And depending on how strong are the similarity or how weak different cases that you would like to use the baseline model to scale up would be certainly one of the parameter that may dictate what would be the best path or the direction that you would go toward looking and trying different transfer learning model. Do you agree,
Exactly.
Mohammed?
Yes, yes. So basically, in terms of AI and data science, it's called feature engineering. So it's very important to first go through your features, and you need to be creative, to understand. That's why I'm saying the data is very important. The targets feature, you need to understand them carefully, and then try to be more creative to go through it, to try different things. You can combine different features as well. And try the model one more time to see if it increases the accuracy or not. Basically, that's feature engineering, and also outlier removals are very important. And standard scaling is very important because, for example, in this data, you have building types which is range between 1 to 4. On the other hand, you have, for example, infiltration rate, which range between 0.002 to 0.5. So it's important to scale your data set before adding to the AI algorithm because it increases the accuracy and balance of the data which end up in having more accurate AI model.
Great. And for the student that, I mean, maybe some of you are more familiar, some of them are not that familiar, but um, in general, the building energy performance is being taken care of by two different categories of model-based technique. One of them is physics-based simulation. We talked about energy plus L debit in this class as a tool that you use some of the input parameters and you use physics and energy conservation in order to predict energy consumption, indoor temperature, etc., etc. Um, so the good thing about energy simulation um, through physics-based um, method is that um, you have a governing equation. And with some assumption, although it is labor intensive, you would be able to take those as the input parameters and predict the energy consumption or temperature, whatever you would be interested to predict. It's it is very similar in other domain areas as well. Another paradigm shift was the introduction of data-driven approaches, like machine learning, deep learning, these approaches, where you use the data. So the data, Mohammed explained a little bit, this could be purely based on simulation-based data versus the measured data or IoT-based monitoring and measured data. So the data-driven approach, one of the biggest challenges in black box modeling was the fact that for building energy performance, there is a parameter that is very important, and that is climate condition, right? So if you develop like a machine learning model in order to predict the energy consumption, that model is very specific to your climate, as Mohammed explained.
Exactly.
For instance, to the climate of London, right? One of the big challenges, and I think what Muhammad um, has done and has achieved in this research is really instrumental because he was able to move the domain of data-driven approaches for building energy prediction to the next step, because we would not just be able to use the actual data, could be measured data or simulated data, to develop and train a model that is highly accurate for that specific case. Now he introduced through transfer learning um, an approach that help scale up the model to different conditions. So different condition could be climate condition. In another case, you can take this and apply this to different building type. So um, yeah, from my perspective, this is really a significant research. Um, and I'm happy that you accepted my invitation to present for us this research. Yeah, that's what I wanted to highlight again about the importance of this research.
That's great.
Any,
I
yeah,
totally
Maha, do you
agree.
want to add anything to it, or is there any other questions from the?
I have a question.
Yes, Ariza.
Thank you, Mohammed, for this speak. That was a great speak. Actually, I have a general question. In transfer learning, how does a pre-trained model identify and use the relevant features from its large, original data set when it's applied to a new task with a much smaller data set? I mean, how does it find the correlation between the older features, and the new ones, and select the useful features? I mean, can you give me
Sure.
an
Yeah,
example?
that's a great question. I'm going to show you on the table here. Here is of the data that we had for London. Okay. So we have, for example, 10 inputs and we're looking for three outputs. Okay. So there's one thing that you need to consider, that the input and output should be the same if you're using transfer learning. So you cannot get the data from somewhere else, which is totally different in terms of inputs and outputs, and you want to try to improve the accuracy of the model. But there is a solution if there is differences between the inputs of the, for example, developed model and the data set you already have. So that's why I'm saying you need to use feature engineering. For example, I'm not sure. For example, you have a, just give me a second. Let me think what I can say. So now uh, you can create from data set a new features called uh, Windows areas per floor area, something like that, WFA, for example. So you can create new features to adjust your current data set to be adjusted to the new data set that you're looking for prediction. So this is what I can tell you at the moment, and also um, engineering. So here, um, again, so if you have the same input and output, so it's easy. So fine tuning of the GBM, for example, it would exactly be like training it from scratch, the same coding and everything. But the model itself, you need to save it before. The model has its own biases and weights, so it already have the every information. Okay, and then you just need to pass new data through, and it will try to fine tune itself based on new data. So that would be my answer. I hope I could answer it well.
Thank you so much.
No worries.
I also have a question. Yeah. First, thank you so much. Oh,
I have.
You got disconnected, Fahad.
am
Can
I
you
audible
hear?
now?
Yeah, you're yes. We
Oh, yeah.
can hear.
Thank you so much, Muhammad. Yeah, it was a really nice presentation. I have a question. It's kind of not relevant to the presentation, but like when it comes to like combining models, it's usually like a bit complex. So I was just wondering, like, if you could recommend a book or a specialized course or something similar that kind of cover these topics in detail. I'm just like asking from your experience, like the things that might have helped you doing this research.
So let me rephrase the question. You're looking for a source to get you the knowledge to work on this type of research, right?
Yes, from your experience, like
YouTube.
what do you like? Oh, YouTube. Okay.
So basically, you can find everything you're looking for. Just try YouTube first, and then again use your creativity and imagination. Then you need to work on it as well. So you're learning from YouTube, and then try to using your own work to bring it to the scene, and then you get improved slowly.
Okay. Thank you.
Yeah,
That,
and
actually, that's the approach
I think you got disconnected, Muhammad. Can you repeat? That was the approach. What? I couldn't hear you.
I'm always using
Okay.
in any new. Yeah.
Okay. I mean that is certainly a good source. I think Fahad's question was also asking a little bit about your thought for combining the models. When you would like to combine the model, or that's my perception. If that was not the question, I would like to ask that question. So, for instance, I mean, you already selected to work with XGBoost and FNN. That was the two first model that you used in both baseline model as well as the transfer learning, and then you combine them. So, I think Fahad asked.
Oh, okay.
Combining this is difficult, and that is a difficult task actually. How you would select what is the best approach to combine this model to come up with something like GBM,
Okay.
right?
So, yeah, basically, if I want to be honest, I got it from experience because working with different machine learning models. So let me be clear. We have some machine learning models and we have deep learning models. So I want to make it,
Mhm.
separate because uh, for working with machine learning, out of my experience applying them in building performance areas, I always found XGB as the best performing model. That's why it's my favorite model right now. And then GBM is it's a little bit time consuming, but again, it has a strong performance like all the time. So that's why I'm always stick with these two models. So and then try to be curious and explore different model as well. But in terms of deep learning, uh, here I use the most simplest deep learning model you could find, which is feed-forward neural network. And the reason was because of the data. If we look at the data, one see these are tabular data. So we don't have any time series data here or any special kind of data. Uh, we have just simple some inputs and outputs, and basically approach here is to go with deep learning models because they need high amount of data and their performance usually are less accurate compared to XGB and GBM in this type of data. This is very important to consider. But if you have advanced data like a sensor that you have time series data like every minute, every 5 minutes, or whatever you're working on, it would be better to go with some other data, some other models like LSTM or AI models. And that's why. So basically, the the data set is tabular for this research, and the best way was to explore machine learning models, and I wanted to be more creative, so I tried to stack these models and improve. And actually, I tried to stack different models as well. But in some cases, it fails. In some cases, the accuracy reduced. But FNN and XGB doing good and improve the accuracy of this um, project. But again, if you apply the same model to a new climate, to a new data with different input and output, the performance would be different. But it's always good to use transfer learning to improve it.
Great. Thank you, Mohammed. Any other questions? No question is probably good sign or not a good sign at all. So.
No, it's always a good sign.
All right. Let's thank you, Mohammed, again for taking the time.
No worries, no worries.
Thank you, Mohammed. Wonderful presentation. Thank you.
Thank you.
All right. So we can wrap up this session, and I hope you guys have a great Thanksgiving break, and I'll see you after the break. Take care.
Thank you all.